Hey everyone, and welcome back to Talk Tensors. Today we are diving into a paper that's tackling a really interesting challenge in AI. Teaching machines, not just to, see objects, but to understand how we humans actually use them.
Yeah, it's a really cool idea.
Yeah, the paper's called David, Modeling Dynamic Affordance of 3D Objects Using Pre-trained Video Diffusion Models.
Yeah. It's a bit of a mouthful. I know.
It is a mouthful, but I am very intrigued, so break it down for us.
All right, so think about how you interact with everyday objects.
Yeah.
Let's say you need to grab your coffee mug from the table. You don't just reach out and grab it any old way, right?
No, definitely not. I've had my fair share of spills grabbing it the wrong way, but I usually grab it by the handle.
Exactly.
Yeah.
You instinctively know the best way to grasp it and lift it and bring it to your mouth for a sip. And that intuitive understanding of how to interact with an object is what researchers call affordance.
So it's like the object itself is giving you cues on how to use it.
Yeah, that's a great way to put it. And for a long time, AI research has focused on teaching machines to recognize and categorize objects, basically understanding what something is. But this paper goes a step further. It's about understanding how humans move with objects over time.
So not just what it is, but how we actually use it.
Precisely. They're calling it dynamic affordance because it captures that dynamic relationship between a person and an object.
Okay, I'm starting to see why this is the big deal, but how do you even begin to teach a machine something as complex as dynamic affordance? It seems like there are endless ways we interact with objects in the world.
You're absolutely right. It's a very complex problem, and that's where this paper gets really interesting. They've come up with a clever solution, using AI to generate synthetic data for training.
Wait, so they're using AI to teach AI?
In a way, yes. It's a bit mind-bending,
Yeah.
but it's actually a brilliant approach. Think about how we humans learn. We observe others, we experiment, we get feedback. And the researchers are essentially replicating that process using AI.
Okay, I'm all ears. Walk us through it.
It all starts with a 3D model of an object. Let's stick with your coffee mug example. Imagine a digital sculptor creating a highly detailed three-dimensional model of that mug.
Okay, so we've got our virtual coffee mug. What's next?
They use this 3D model to generate a whole bunch of images of the mug from different viewpoints. It's like taking a 3D scan of the object, capturing every angle in detail.
So far, so good. But where does the dynamic affordance come in?
That's where another AI comes in. They use a powerful tool called ControlNet, along with a pre-trained 2D diffusion model to create images that show people interacting with the mug from those different viewpoints.
Hold on, are you saying they're using AI to basically imagine how people would use the mug?
You got it. These AI models have been trained on massive data sets of images and videos, so they have a pretty good understanding of how the world works and how humans interact with objects.
Wow, that's pretty wild. So they're using AI to essentially generate a whole library of virtual interactions with the coffee mug.
Exactly, but they don't stop there. They take those images and turn them into short 2D videos, showing the person's movements as they pick up the mug, take a sip, and so on.
Okay, I'm picturing these little animated clips of someone using the mug. But how do they go from those 2D videos to teaching an AI about dynamic affordance in the real world?
This is where the real magic happens. They've developed a technique to uplift those 2D videos into 3D representations. It's a complex process involving things like world-grounded human motion recovery and 2D to 3D correspondence finding.
Okay, you're starting to lose me with the technical jargon. What's the bottom line? What do they end up with?
Essentially, they create these incredibly detailed 4D representations of human-object interaction. It's not just a 3D model of the mug anymore. It's a 3D model of the mug and the person interacting with it with accurate movements over time.
Okay, now that is impressive. So they've essentially created this whole virtual world of human-object interactions. But how does that actually teach an AI about dynamic affordance?
That's where their new AI model comes in. They call it David.
David, like the sculptor. Is there a connection there?
It's a clever name, right? And it's actually quite fitting. You see, David is like a student learning from those 4D representations we just talked about. It's trained on all those synthetic videos of people interacting with different objects, and it starts to pick up on the patterns.
So it's like David is watching these virtual demonstrations and learning by example.
Exactly. It's learning how the shape of an object influences the way we move, how our movements affect the object's motion, and all those subtle nuances of human-object interaction.
This is all starting to sound very sci-fi to me.
Oh.
It's like they're creating robots that can learn by watching us.
Well, we're not quite at the robot butler stage yet, but this is definitely a big step in that direction.
So David is the star of the show here. Can you tell us a bit more about how it actually works? What's under the hood?
Sure, David is actually composed of two main parts, a LoRa module and a human-conditioned object pose diffusion model. Now, I know this sound like complicated terms.
Yeah, a little bit.
Okay.
Can you break them down for us non-AI experts?
Absolutely. The LoRa module is all about customizing human movement for specific objects.
Okay, like adapting a general understanding of how humans move to the specifics of, say, picking up a coffee mug versus throwing a baseball.
You got it. And the object pose diffusion model is what predicts how the object moves in response to those human actions.
So it's like a two-way street. The human influences the object, and the object influences the human.
Exactly. And that's a crucial part of understanding dynamic affordance. It's not just about the human dictating the interaction. The object itself plays a role in shaping how we use it.
This is making me think about those videos of robots trying to do human tasks and failing miserably.
Yeah.
It's like they're missing that understanding of how the object pushes back, so to speak.
Right. They might know how to grasp something, but they don't necessarily understand the subtle adjustments and reactions needed to actually use it effectively.
Okay, I'm really starting to grasp the significance of this research. They're not just teaching AI to see objects, they're teaching it to understand the whole dance of human-object interaction. This is really cool.
I agree. It's groundbreaking work. And the fact that they're achieving this using synthetic data is a game changer.
Before we move on, can you remind us why synthetic data is such a big deal?
Sure, traditional AI training often relies on huge data sets of real-world images and videos. But collecting and labeling that data is incredibly time-consuming and expensive.
And sometimes it's just not possible to capture all the variations and complexities of real-world interactions, right?
Exactly. But with synthetic data, you can generate as much data as you need in a controlled environment and tailor it to specific tasks.
So instead of trying to film every possible way a person might use a coffee mug, they can just generate those interactions virtually. That makes a lot of sense.
It's a much more efficient and scalable approach, and it opens up a whole world of possibilities for training AI on tasks that would be impossible or too dangerous to capture in the real world.
I'm starting to see the potential here. This could revolutionize everything from robotics to virtual reality to even animation. But before we get too carried away with the possibilities, I want to make sure we understand how well David actually performs. The paper mentions some pretty impressive results, right?
They do. They actually compare David to another state-of-the-art model called OMO, using a data set of real-world human-object interactions. And what's really remarkable is that David trained on synthetic data actually outperforms BOMO on several key metrics.
Wow, so it's not just a cool concept, it actually works in practice.
Yes, it's particularly good at capturing the realism of human motion and accurately predicting those subtle contact points between the person and the object.
So it's not just moving in a vaguely human-like way, it's actually capturing the nuances of how we interact with objects in the real world.
Exactly. And that's incredibly important for building AI that can interact with our world safely and effectively.
This is truly groundbreaking stuff. Before we move on, let's take a moment to recap the key takeaways for our listeners.
Absolutely. I think the big takeaway here is that we're witnessing a paradigm shift in how we think about AI and its ability to understand and interact with the physical world. Dynamic affordance offers a powerful new framework for building more intuitive and capable AI systems.
And the fact that they're achieving this using synthetic data makes it even more exciting because it means this technology has the potential to scale up and be applied to all sorts of different objects and tasks.
Precisely. It's a really exciting time to be following this field of research.
Well said. Now, I know you've got some really interesting thoughts on where this research could lead in the future, but we'll save those for our Novel Notions segment. Stay tuned.
Welcome back to Talk Tensors. You know, before the break, we were just diving deep into this world of dynamic affordance and this idea of, teaching AI not just what objects are, but how to use them, like we humans do.
Right. We were talking about this new AI model, David, that's learning all about human-object interactions from these amazing 4D simulations they created.
Yeah. And remember, what's really groundbreaking is that David is trained on synthetic data, meaning it can learn about any objects you can think of without needing tons of real-world examples.
Which opens up so many possibilities.
Right.
Okay. So let's get back to the paper itself. There's this section on concept merging that I thought was super interesting. It sounds like something straight out of a sci-fi movie.
It does sound kind of futuristic, doesn't it? But the idea is actually pretty straightforward. Remember how we talked about David having this LoRa module that allows it to adapt its movements to specific
Yeah,
objects?
like learning the difference between picking up a delicate wine glass
Yeah,
versus grabbing like a heavy toolbox.
exactly. Well, concept merging takes that idea a step further. It allows David to combine those learned concepts from different objects to create interactions involving multiple objects.
Wait, so you're telling me it can learn to use two objects at once, like juggling or maybe playing the drums?
You're on the right track. The researchers use the example of a scooter and an umbrella. By combining the LoRa's for these two objects, they were able to generate a video of someone smoothly riding a scooter while simultaneously holding an umbrella.
Wow, I'm looking at figure 7 now, and it's amazing how realistic it looks. The person is steering with one hand, holding the umbrella steady with the other. It's like watching someone navigate a rainy day commute.
Yeah, it is pretty remarkable. And what's really exciting is that this opens up the possibility of teaching AI much more complex and nuanced interactions.
Yeah, I'm already imagining the possibilities for robot assistance.
Yeah.
Imagine a robot that can not only fetch you an umbrella when it rains, but can also hold your coffee while opening a door for you. It's like having a personal butler.
Now you're getting it.
Yeah.
This concept merging capability takes us a big step closer to that vision of AI seamlessly integrating into our daily lives and helping us with all sorts of tasks.
Yeah, I am officially blown away, but as always, I'm curious about the limitations. The researchers are pretty upfront about the challenges they encountered, which I appreciate.
Yeah, transparency is key, especially in cutting-edge research like this. One limitation they discuss is the potential for spatial bias in the 2D image generation process. Remember, they're using ControlNet to create those initial images of people interacting with objects.
Right, it's like giving the AI a template to work with.
Exactly. And because of how certain pre-trained models work, there can be a bias towards placing objects in specific locations within the image. This can sometimes lead to results that don't quite make sense.
So like if the model is biased towards placing umbrellas in the top right corner of the image, it might struggle to generate a scene where someone is holding an umbrella properly at their side.
That's a good example. And this highlights the need for ongoing research into mitigating these biases in AI models.
Mhm.
We want to make sure these systems are as flexible and realistic as possible.
Absolutely. I also
Cool.
noticed they mentioned a limitation related to something called smoothness guidance sampling, which is used to generate the object's motion trajectories.
Ah, yes, that's a fascinating point. Most object movements during interactions tend to be relatively smooth and continuous. That's the assumption built into the smoothness guidance sampling technique.
Makes sense. But of course, there are always exceptions to the rule.
Precisely. If you're thinking about actions like hammering a nail or shaking a bottle, those movements are much more jerky and unpredictable. The current model might have difficulty accurately capturing those more erratic motions.
So it's like the model is a smooth dancer, but it hasn't quite mastered those breakdancing moves yet.
That's a great analogy. And this is another area where future research could push the boundaries. Developing techniques that can model a wider range of motion dynamics would be incredibly valuable.
It's like teaching the AI to dance to all genres of music, not just waltz.
I love it. Expanding the AI's repertoire of movements is definitely key.
Speaking of complex movements, they also mentioned some limitations in modeling how our hands interact with objects.
Yeah.
It seems like our hands, with all their dexterity, are a real challenge for AI to replicate.
You're absolutely right. Hands are incredibly complex and versatile tools. While AI has gotten incredibly good at recognizing and generating images of hands, accurately capturing the fine-grained details of how they grasp, manipulate, and interact with objects is still a very difficult problem.
Yeah, it makes sense. Our hands have so many joints and degrees of freedom.
Exactly. And then you add in the dynamic element, how our fingers move and adjust in real time as we interact with different objects. It's a massive computational challenge.
So while the paper shows some impressive results in generating overall human-object interactions, there's still work to be done in capturing the intricate dance between our hands and the objects we use.
Absolutely. But this is where advancements in areas like hand pose estimation, 3D modeling, and motion capture will play a crucial role in pushing the boundaries of what's possible.
It's exciting to think about how all these different fields are converging to create these increasingly sophisticated AI systems. It's like a symphony of technology and innovation.
It really is a collaborative effort. And I think this paper beautifully highlights how interdisciplinary research is essential for driving progress in AI.
Before we dive into your novel notions segment, I want to touch on one more limitation. They mentioned concept conflict. It sounds like something straight out of a superhero comic book.
It does have a certain dramatic flair, doesn't it? Concept conflict essentially refers to the challenges that arise when you try to combine those LoRa modules for different objects.
Yeah.
While merging concepts can lead to creative new interactions, it's not always a smooth process.
So like trying to mix oil and water, some concepts just don't blend well together.
Exactly. If you try to combine the LoRa for a barbell with the LoRa for a shopping cart, for instance, the AI might generate some awkward, nonsensical movements. It could try to lift the shopping cart like a weight or push the barbell like it's on wheels.
That would definitely make for some hilarious bloopers.
Yeah,
But in terms of real-world applications, that's obviously something you'd want to avoid.
absolutely. And this raises an interesting research question. How do you determine which concepts are compatible and how to guide the merging process to ensure the AI generates realistic and meaningful interactions?
It's like trying to write a recipe by randomly combining ingredients. Sometimes you create a culinary masterpiece, and sometimes you end up with a dish that's best left uneaten.
I love that analogy. Just as a skilled chef knows which flavors complement each other, we need to develop methods that can guide the merging of these conceptual building blocks in AI, ensuring the results are coherent and functional.
Well, I think this paper has given us a fascinating glimpse into the incredible potential of dynamic affordance and the exciting research pathways it's opening up. Now I'm even more eager to hear your novel notions. What mind-blowing ideas have you been cooking up?
Get ready for some serious conceptual fusion. This paper got me thinking about a concept called embodied cognition.
Embodied cognition. That rings a bell, but I'm a bit rusty on the detail.
It's the idea that our minds aren't just these abstract information processors, but are deeply intertwined with our physical bodies and how we interact with the world. Our experiences, our movements, our senses, they all shape how we think and learn.
Right, it's like that classic mind-body problem, but with a more well-embodied perspective.
Exactly. And what's fascinating to me is that dynamic affordance seems to be a perfect example of embodied cognition in action. It's all about understanding how our physical movements influence how we understand and use objects.
So you're suggesting that by studying dynamic affordance in AI, we might actually gain insights into how our own minds work.
That's my thinking. It's like holding a mirror up to ourselves, using AI as a tool to reflect on our own cognitive processes. And this leads me to my first novel notion. What if we could use models like David to actually study and understand human cognitive development?
Okay, that's an interesting twist I wasn't expecting.
Mhm.
How would that work in practice?
Imagine using David to create virtual environments where we can simulate how infants and children learn to interact with objects. We could test different theories of cognitive development, observe how these virtual agents learn and experiment and compare their behavior to real-world data from children.
It's like building a virtual playground for AI babies.
Exactly. And because these virtual environments are so controllable, we could test different variables, manipulate the objects in the environment, and gain insights that would be difficult or impossible to get from traditional observational studies with real children.
I can already see the headlines. Scientists teach AI to play with blocks, unlock secrets of human development.
And the applications extend beyond basic research. Imagine using these simulations to create personalized training programs for children with developmental delays, or to design more intuitive and engaging educational tools that adapt to a child's learning style.
Wow, that's incredible.
Yeah.
We're talking about using AI not just to mimic human behavior, but to actually deepen our understanding of how our minds learn and grow.
And that brings me to my second novel notion, which builds on this idea of using AI to understand human cognition. What if we could use dynamic affordance models to create AI systems that are not just intelligent, but also possess a sense of embodiment?
Embodiment in AI. Okay,
Yeah.
I'm definitely intrigued. Tell me more.
Think about it. Right now, most AI systems are essentially disembodied minds. They exist in the digital realm, manipulating data and algorithms, but they don't have any real connection to the physical world.
It's like their brains in jars without any limbs or senses to experience the world directly.
A perfect analogy. But what if we could change that? What if we could create AI systems that have virtual bodies that can learn and interact with the world through simulated senses and that develop an understanding of affordances through embodied experiences just like we do?
So instead of just processing information abstractly, they would learn through simulated interactions like picking up objects, navigating spaces, experiencing the world through virtual senses.
Exactly. And this could lead to a whole new level of AI sophistication. Imagine AI systems that can not only solve complex problems, but that can also understand and relate to human experiences in a much deeper, more intuitive way.
AI that can empathize with us, that can understand our emotions and motivations because it has experienced the world, even if virtually through a similar lens. That's a powerful idea.
It is. And that's the truly exciting part of this novel notion. It's not just about building smarter AI, it's about building AI that is more human-like in its ability to understand and navigate the complexities of the world and our place within it.
This is venturing into some pretty profound territory, but it's also incredibly exciting. I'm already buzzing with ideas.
Yeah.
But before we get too lost in the possibilities, what kind of research would actually be needed to bring these embodied AI systems to life?
It's definitely a grand challenge, but not an insurmountable one. We'd need to significantly advance our capabilities in areas like virtual embodiment, sensory simulation, and developmental robotics.
So recreating the entire human experience in a virtual world, a tall order for sure.
It is a complex undertaking, but even small steps in these areas could yield significant breakthroughs. Imagine developing virtual environments where AI agents can learn to grasp objects, navigate obstacles, interact with other agents, all in a physically realistic way.
It's like building a virtual playground for AI where they can learn and grow through embodied experiences just as children do.
That's a great way to put it. And by studying how these AI agents learn and adapt, we could gain valuable insights into human cognition and development, which could then inform the design of even more sophisticated and human-like AI systems.
This is a research area I'll definitely be keeping my eye on. It has the potential to revolutionize not only AI, but our understanding of ourselves as well.
Yeah.
But as you always remind us, these novel notions are just that, notions, ideas to spark discussion and inspire future exploration.
Precisely. And it's
Yeah.
important to remember that we're still in the early stages of understanding both dynamic affordance and embodied cognition. But I do believe that by combining these two powerful concepts, we can unlock new frontiers in AI research and development.
Welcome back to Talk Tensors. So we've been on quite the journey today, exploring, this fascinating concept of dynamic affordance, teaching AI, not just what objects are, but how we actually use them, like humans do.
Yeah, it's like giving AI a crash course in, the unspoken language of human-object interaction.
Exactly. And I really enjoyed your novel notion segment in the last part, using AI to study human development, creating AI with virtual bodies and senses. Really incredible stuff to think about where that could lead.
Yeah, the possibilities are really exciting. But before we get too far ahead of ourselves, there's one more aspect of the paper I want to touch on. It's something they call the importance of context in understanding dynamic affordance.
Okay, context. I have a feeling this is a big one. Help me understand what they mean.
Sure. So think about it this way. How you use an object isn't just determined by the object itself, right? It's also shaped by the environment you're in, your goals, even your past experiences.
So like a hammer has different affordances depending on whether you're building a house or trying to crack open a walnut?
Perfect example. And the authors argue that truly intelligent AI needs to be able to take this context into account. It's not enough to just know how to swing a hammer. You need to understand when, where, and why to swing it.
Yeah. This makes me think about all those viral videos of robots failing miserably at seemingly simple tasks. It's like they have the mechanics down, but they lack the common sense to apply those skills appropriately.
Yeah, it's like they're missing that human intuition. We instinctively know a hammer isn't the best tool for eating soup, but a robot might not have that same inherent understanding.
So how do we teach AI this contextual awareness? Is that even possible?
It's a challenging problem for sure, but I think there are a few promising avenues for research. One approach is to incorporate more diverse and realistic environments into AI training. Instead of just learning in these sterile simulated worlds, we need to expose AI to, the messy complexities of the real world.
So like training a robot chef in a real kitchen with all its clutter and chaos instead of just a perfectly organized virtual one.
Exactly. That way, the AI would learn not just how to use a knife, but also how to navigate around obstacles, anticipate potential hazards, adapt to unexpected situations.
It's like giving the AI a crash course in real-world physics and common sense.
Right. Another important aspect of context is understanding human goals and intentions. We use objects to achieve specific aims, and AI needs to be able to infer those goals in order to interact with us effectively.
So if I pick up a hammer and walk towards a nail sticking out of the wall, the AI should be able to infer that I'm probably about to hammer that nail in, not use it as a makeshift back scratcher or something.
Precisely. And this requires the AI to not just recognize objects and actions, but to also understand the relationships between them and the underlying goals driving those actions.
It's like teaching the AI to read between the lines to understand the why behind our actions.
Exactly. And this is where advancements in areas like natural language processing, human-robot interaction, and even psychology could play a crucial role.
It's fascinating to see how all these different fields are coming together to tackle this challenge of building truly intelligent AI.
It really really is a multidisciplinary effort. Understanding human behavior and cognition is a complex undertaking, and translating that understanding into algorithms and code is even more challenging.
But the potential rewards are immense. Imagine
Oh,
AI that can understand context, infer our intentions, and act accordingly. It would revolutionize so many aspects of our lives.
yeah, we're talking about AI that can truly collaborate with us, anticipate our needs, and help us achieve our goals in a way that feels natural and seamless.
It's about moving beyond AI as a tool and into the realm of AI as a partner.
I couldn't have said it better myself.
Well, I think we've given our listeners a lot to chew on today. This paper has opened our eyes to the incredible potential of dynamic affordance and the exciting research directions. It's paving the way for it. It's clear we're just at the beginning of this journey, but the possibilities are truly mind-boggling.
I completely agree. And as always, we encourage our listeners to check out the full paper in the show notes. There's so much more to explore.
Absolutely. Thanks for joining us on this deep dive into dynamic affordance. Until next time, keep those neural networks firing.